Hi and welcome to AI Sweden, the Swedish National Center for Applied AI. Welcome to the recording online and welcome here. My name is Nina Åquist and I'm the head of the NLU team. And we are really pleased to welcome Josef Lindman Hörnlund, who is here today and will be properly introduced soon. So thank you for being here.
And now it's time to introduce our speaker, the reason why you're all here. And I think that there is no better way to start the year, if not with a little status check and a little prediction. Today's guest is Josef Lindman Hörnlund, co-founder and CEO of Modulai. Josef is, you say, very, very close to AI research, and you follow papers, benchmarks, and industrial outcomes and technical results as they appear, while at the same time staying hands-on, working hands-on with AI systems and testing AI systems, building and testing. So today the focus is that we will hear what has actually changed over the last year, and what recent results show, and where research progress and industrial reality currently line up. And I want to warn you all that in the past, in previous talks, what Josef has pointed to early has later become true. So I'm really, really happy that you can share your insights with us today. Over to Josef.
Thank you so much, Daniela. So let's see. First of all, these slides are handwritten, and it's in a world where AI is generating a lot of material. I think it's a good point to actually show you that these were not AI generated. I've written them by hand. So, and if you don't like my writing, I'm happy to tell you a little bit more exactly what it says. But the point here is to give them a little bit more personality and really show that this is my opinions, and yeah, I think I can stand behind most of it. Yeah, so I put this very ambitious title, where AI research and industry stand right now and what we should expect in the coming year and years. And I regretted that a little bit because I will absolutely not cover all of it. There is a lot of things that I will not talk about. For example, embodied AI, or anything machine learning or AI related to the physical world. We will primarily only talk about language models and their application in the digital world to solve business problems that can be translated into, digital data in and digital data out. And we will primarily focus on post-training and what people actually do with the language models after they have been pre-trained, because that's sort of where most of the research is right now. Yeah, just brief. Modulai is a consultancy firm, super niche, 30 people approximately, 25 machine learning engineers helping companies build the kind of systems that we're talking about today. A lot of agents over a couple of years, but back in the days we did a lot of machine learning, predictive analytics, and so on. Okay, so the agenda. I will first be setting the scene a little bit, and primarily we will talk about something that is called the economic Turing test. I don't know, I don't know if you've heard of it, but we will go through it in detail. And then a little bit of discussion about pre-training, post-training, and talk a lot about where the data is going to come from. I don't know if you saw this article in Svenska Dagbladet before Christmas, I think it was. It was like a clickbaity article where they claim that AI is close to collapse because we're running out of data. And there was some discussion from some experts in that paper about, okay, maybe there is some data that is actually available to take the models to the next level. And I think a lot of this talk is actually about that. AI and machine learning has always been about the data, and where the data is going to come from and how we train it is sort of always what takes you to the next level. And this is going to be a fairly technical talk. No equations, but almost. And we will talk about a couple of technical terms like reinforcement learning primarily. So if you know what that is, that's going to be beneficial, but it's not necessary. And then all these different reinforcement learning techniques that people are using right now in order to actually take the models to the next level. in particularly in the situation of the economic Turing test. And then a little bit of discussion about what's next. So here is actually what it says there is by which we mean highly autonomous system that outperform humans at most economically valuable work. And it's OpenAI's mission. And what we mean with outperform humans at most economically valuable work, that's sort of their definition of AGI, and that's also part of the contract they have with Microsoft, for example. When they said that when you have AI systems that can produce a lot of money, then we have reached AGI in some sense. And today we will talk about how far are we here and what will it take to get there, basically. And that's the reason for the ambitious title. So, the economic Turing test. So this was defined by one of the co-founders of Anthropic, but he's not the only one. There's different variations of this. But basically, it is, he talked about it on a podcast that I can recommend that is called the No Priors podcast. A lot of it is with high-profile AI people. And basically, you have this problem of, you take a hiring manager, and that hiring manager will hire both an AI and a human for some economically valuable task. And you let them work side by side for a month to do exactly the same thing. And if the hiring manager picks the AI for 50% of all the economically valuable tasks in the society, you have passed the economic Turing test. So it's a very practical definition to say that basically if for 50% of all these tasks, you can replace the human. And that's very similar to OpenAI's definition, where you basically outperform humans at most economically valuable tasks. And so I don't know, I think I really like this definition because it really makes the systems, you need to see their application in the real world. And one thing, this is one of the definitions of AGI that people have. In this DeepMind paper, position paper they had, the DeepMind had a couple of different definitions of AGI. This is one of them. But I haven't seen it talked about that much, which is surprisingly. So now hopefully you, at least in this call, and in here, will be able to remember this and think about this. So, okay, skip that one and that one. Okay, so the real test is, of course, this is the real test. And this will happen in industry. But before it actually happens, we need benchmarks. So first I will go through a couple of benchmarks. And this is a paper that came out from Carnegie and Duke, I think in the beginning of last year. They have this agent company. And in the text, it says, in this paper, we introduce the agent company, an extensible benchmark for evaluating AI agents that interact with the world in similar ways to those of digital worker, by browsing the web, writing code, and running programs, and communicating with other coworkers. So this basically simulates a software company in a multi-agent environment. So you would have different coworkers that have different roles. It would be someone in the finance department, someone in the HR department, some software developers, some project managers, and so on, and you build a benchmark environment where they need to solve true economically valuable tasks in that environment. That could be, for example, to release a new feature. So an example task here is that we have input and access some sprint issues in a ticketing system, and they have some chat. You need to talk about, notify the issues to the people that are involved in implementing this issue, maybe clone the repo, get the code, implement the new feature, and then incorporate feedback on that new feature from your manager. And that could be an example task in this agent company benchmark. And so let's remember, always have the economic Turing test in the back of your mind here now. So Gemini 2.5 Pro, this came in the summer, so it's a little bit older model, but that model handled approximately 30% of the tasks in this benchmark. So if you just look at that number, you would say that we're fairly close from the economic fairly close to the economic Turing test. But this is, of course, a very, very limited scenario where the tasks are super well specified and it's mostly related to coding. And if I look at that, we need to remove this one. I can do that. If you look at the different categories of the tasks that the model is actually able to perform in, it's mostly related to software development. So the high bars are software development, project management, and then some HR tasks. But it fails mostly on general data science, that's the DS, admin tasks, and finance and other tasks. So you can see here that it's actually not basically only coding and software development tasks that this agent company test benchmark actually is about, and that's what the models are good at. And there's a good reason for that. Okay. The next benchmark that people use is something that's called GDP eval, and that's actually came out from OpenAI last year on evaluating AI model performance on real-world economically valuable tasks. And the reason why they do this is, of course, it's very close to their definition of AGI and what the company is about, what their charter is. So tasks are constructed from representative work of industry professionals, which an average of 14 years of experience. So they have talked to experts to sit down and create these tasks, very detailed tasks that the models should be able to solve. And as I mentioned, these tasks are always single turn, so that's also a restriction. And it's always digital documentation in and digital documentation out. So basically you get some design specification and you need to produce something from that. And we have two examples here. Recreation worker, optimize the table layout for spring vendor fair. Could be an economically valuable tasks that they have here in the set. And they also have customer service, email response to dissatisfied customers requesting a return. So those are examples that they have in this GDP eval benchmark. And in this task, they actually published a result. And what actually made rounds with this one is that OpenAI published a paper where the anthropic model was the best, which sort of gave a sign that they actually did something real here. And according to the tests, they said that the parity with the industry experts is 50%. The experts could handle 50% of the tasks. Or rather, no, okay, this is actually pairwise comparison. So it's a win rate between the AI and the human. So if it's 50%, then the expert choose the AI solution in 50% of the cases. And if they're equally good, it would be random. So that's why it's 50%. And this was also an older model, Opus 4.1, and it managed to have a win rate of almost 48%. So also very close to parity with a human. Which, of course, is part of this creating a hype of how close we actually are to replacing people in industry. But this is also a very, very limited set of tasks. It's a base model, and they have this agentic harness that helps the model solve these tasks, where they have some prompting that they claim is not overfit to the GDP eval, but of course you can question that. And it's single turn, only digital documents in and out. Okay. And now I think we have the latest test that came in October 2025, which is called the Remote Labor Index. Okay, I cannot remove that one. Anyway, it's a paper that came from the Center of AI Safety and Scale.ai, where they basically say how much of remote work can AI systems automate right now. And this is an example of a task. Develop architectural plans and a 3D model for a container home based on existing PDF design. And in this, these are more complicated tasks in this benchmark. They are not necessarily single turn, and they are multimodal and a lot more advanced than what we saw before in the agent company in the GDP eval. And in this test, the models only passed 2.5% of the tasks. So depending on how complicated you make it for them, you get different pictures of how close we actually are. But these are very difficult tasks in this one. And of course, benchmarks need to always increase the difficulty so that you have something to aim for. Okay, so that's basically the background. There's some different indications, but probably we're quite far from being able to automate most economically valuable work at this point in time. So what basically happens now, and what can we do, and what is industry doing in in solving that. And I think everybody heard about the pre-training being dead. We're out of data from the internet, so we have no more data to train models on. And that's sort of the background of this article in Svenska Dagbladet, that AI is close to collapse because we don't have more data. And Ilya Sutskever, one of the sort of leading prophets of AI and the leading researcher, he talked at NeurIPS, the big AI conference in 2024, that says that pre-training is dead. We had one internet, we're out of that. And now we need to come up with other things to do. And what people started doing that is to introduce this big domain of post-training. And O1 and all the reasoning models that came out, a little bit more than a year ago, was the next step. So you can both you scaled up test time compute and the post-training when pre-training died in some sense. A lot of people still work on pre-training, and it's an important area. You need to curate the data sets, and you can get model improvements and so on from that, but it's not what will take us to the next level. The post-training is currently what will take us to the next level. And we had this DeepSeek moment that actually DeepSeek showed primarily that the Chinese would be able to do this, but also that with fairly simple technique, we had new avenues of building this model. That reinforcement learning can enable further scaling. I call that the DeepSeek moment. A little bit around a year ago. And I have this graph here basically to say that, okay, pre-training took us one step, and now the question is, are we about to plateau, or are this exponential increase in performance going to continue? And hopefully you have some ideas about that during this talk. Okay. So post-training, what's actually post-training now? First of all, I have a graph here that came from XAI in terms of Grok 4. And in the press release for Grok 4, they said that they had spent the same amount of compute to post-training as they did to pre-training. And the big difference when they went from Grok 3 to Grok 4 is basically that they spend a lot of money on the post-training. And this is also probably what the other labs are doing right now, OpenAI and Anthropic and so on. They already have their pre-trained models, and now they spend all the time on doing reinforcement learning on those models. And we have 3 different techniques for that. Reinforcement learning from verifiable rewards, RLVR, which is basically the model generates an answer to a task, and that question can be checked automatically. You get the reward that you use for reinforcement learning without the human actually labeling that answer to see if it was correct or comparing with some ground truth data. But you have problems where you can verify the solution automatically. A good example is math. I give you an equation and you try to solve that equation, and if the math actually works out, you can verify that the solution is correct. Coding is another example of where you have that. You have some test cases for each of the problems, and you can check the code that the model is writing, and you check that automatically, and that gives the reward signal for the reinforcement learning agent to improve. Very important. And then we have reinforcement learning from human feedback, which is what people did before, like ChatGPT was basically a result of that technique, where we use human labels to train a reward model that is used for the generated answers from the model to give a signal to if the model is generating the right thing or not. But the huge difference here is that RLHF needs human input, human labels, and RLVR in some sense doesn't. And the third technique that people are using right now is reinforcement learning from AI feedback, basically where you write down some policy documents, what's also called rubrics, that you say that, okay, an answer is correct if it fulfills the policy that I have in my document. That could be, for example, that if you have a research task, you can say that one of my rubrics, one of my policies is that all the quotes that you have should have a citation and the correct reference. And you should be able to check that reference. It's a task that you can automate, but a human has written exactly what a good answer looks like. And that gives you the reward that you then use for reinforcement learning. And this setup is basically, I put it on a scale here, where you have from RLHF, where you need a lot of human input in order to create the reward signal, to RLVR, where you basically need very little human input to some extent. It's in quotation marks, because we will see later that there is going to be some human input. Most of the data that we use come from humans in the end. But still, it's a scenario that it's going to be much easier to scale, because you don't need humans to provide the reward signal to the same extent as for the other techniques. So this is basically what people are doing. And this is what most of the labs currently spend most of the compute and money and research on, improving these techniques and finding new data sets that can improve this in different domains. Okay, so a good example so we all know that research has been closed now. The big labs doesn't publish what they're doing to that large extent, so we'll have to look at what's published. And the Chinese publish a lot more of what they're doing. For example, the Minimax paper. This is a technical report from the summer, scaling test time compute efficiently with lightning attention, and they basically discuss exactly what they do in order to improve the model in terms of these different techniques here. Different problems and environments for reinforcement learning, verifiable and non-verifiable problems, mathematical reasoning, competitive programming problems, logical reasoning problems, software engineering, see more here, non-verifiable problems like question answering, creative writing, and so on. And here you can see the difference here. The non-verifiable problems, they use reward models, either coming from AI feedback or from human feedback. And then in this logic, math, and coding, and so on, they use verifiable rewards. And this is, okay, and we always need to remember this is the context of the economic Turing test here. This is basically to train the models in all the different aspects that we think can be economically variable, like creative writing, question answering, software development, and so on. And this is a fairly small model, but they used 3 weeks of 512 H800s, so that's the big GPU from NVIDIA, and the cost for this was approximately $500,000. But it's a small model and it's not a lot of data, but still a lot of money. Yeah, I hope the thread is clear here that we're going from the economic Turing test to the post-training techniques, verifiable, non-verifiable domains, and we try to build models that actually can solve these economically valuable tasks. Okay, and so this is in terms of scaling and cost. So we all know that everybody's building data centers like crazy right now. And you're thinking basically, if we don't have data, what should they use these data centers for? And this is the answer. So this is a paper also coming out from NVIDIA. Prolonged reinforcement learning expands reasoning boundaries in large language models. And they have 134 tasks that they collect: math, coding, STEM, logical puzzles, and instruction following. So very verifiable, quantitative domains. And they use 16,000 GPU hours on 48 H100s for this in order to train the model. So, and it's a very, very limited data set. But you can see it's a lot of compute still. And it's because reinforcement learning is very sample inefficient and it's very complicated engineering and so on to set this kind of thing up. Okay, so what's so special with coding? And I hope that you all know now we have this Opus 4.5 moment. I think I saw that on LinkedIn that people called it like that, or the anthropic moment or something like that, because with the latest Anthropic and OpenAI models now, a lot of engineers say that, okay, this is a big shift in terms of how good the models are at programming. So now software developers maybe we are at the moment where we can actually use these models to write code in a good and efficient way, and most people are actually going to realizing and sort of accepting that in some sense. And the reason is that coding is a verifiable problem. So you can write these test cases, you can do type checks, you can do compilation, and you can scale it up to in a reinforcement learning setting with a lot of data that we will talk about soon, so that you can use these big data centers in order to train these models to actually be really good at coding without having a human going in and checking all the code and so on. So you do this by creating a sandbox with all the right code, the dependencies, the development tools, and you basically put the agent or the language models in that sandbox and let them try to solve programming tasks. And you check the answers if the test cases pass. Right. Okay, so where does the data come from? And there's a lot of work on this, but this is also a good example. It's a paper called R2E GIM, Procedural Environments and Hybrid Verifiers for Scaling Open Weights Software Engineering Agents. It's from UC Berkeley, primarily. And basically what they show in this paper is that you can take a public GitHub repo, and you can take that repo and you can create verifiable reinforcement learning tasks automatically from those reports. They claim we procedurally generate training environments using only commits from GitHub repositories, reducing reliance on both human written issues and test cases. Okay, and how much data is that actually? Okay, I looked it up on GitHub. They say that there is about 400 million public GitHub repos. We have 10 million PRs merged per month, and there's 200 million commits that were made in public repos approximately during 2025. So if you say that each of these commits can be, you can create one or more reinforcement learning tasks from that, and we know that that will improve the model, we have a lot of data. So when people claim that we're running out of data just because we ran out of internet, that's absolutely not true. So, and why everybody is talking about code right now is basically because there's a lot of data, we have the techniques that is necessary, reinforcement learning from verifiable feedback, and we have a lot of compute, and we have a good prior in terms of the language model in actually to train it. So this is the sort of the reason why we're having this opus moment right now. And of course, in terms of the economic Turing test, we know that software development is a big part of the digital economy. So I don't know how much, of course, but it's basically going to be a lot of software development and feature building and app creation and so on. We have, Lovable and all these things that is changing the way we do software development. Okay, so it's clear that coding is a very special field. We have a lot of data from all the code that is humans have written. So that's why actually this, when we say that it's no human inputs, it's wrong, because we need to have humans needed to have made those commits to begin with. And that's exactly like with pre-training, that pre-training is of course based on data that was out there, that human wrote those texts. So I mean, this is a very similar scenario, but we can scale it up in the same way that we scaled up pre-training. Okay, so of course coding is only a very particular problem. So another thing that I think is very interesting is that Anthropic came out with a partnership, I think in a month ago, where basically they partner with a company called Diode Computing that do printable circuit boards. And printable circuit boards is of course another economically valuable task because we have a lot of hardware to make. And they have built a language called Zener that is a domain-specific language for how to design circuit boards. So, and you can make that task, designing a circuit board, you can make that verifiable by writing the circuit board in this language and then checking if the solution is correct by using a design specification that you send signal into the circuit, and you check if the circuit is producing the right output. And if you have a design specification that tells you how that circuit should work, you can train an agent through reinforcement learning again to design these circuit boards. So we have taken economically valuable tasks and we have turned it into a problem that is amendable to the techniques that we have for post-training, basically. So data scales here with the design, how many design specifications we have. So it's not the same as with code, that we have like millions of printed circuit boards written in the specifications for those out on the internet. So this is not going to scale in the same way. Important difference, but still we have the technique now for actually being able to automatically generate the specifications for circuit boards, and we can use that to create new hardware. Okay, so that's an example of where we have verifiable techniques, but not necessarily the amount of data. And my third example here is patient diagnosis, where a medical diagnosis is not digitally verifiable. I cannot basically come up with it. If you come with me and you have a cough and you have back pain, and I say that that's probably, cancer, and I cannot verify that automatically. I need to do lab tests. I need to check on pictures that I take from the inside of your body to see if it's actually a cancer. And here we cannot use the technique of verifiable reward. But we can use human feedback, for example, or we can use reinforcement learning from AI feedback by having policy documents to say that the diagnosis should fulfill a certain set of criteria, which means that you basically have done the necessary laboratory tests, you have looked at all the scans, brain scans or body scans, and you have made a verifiable or a diagnosis that is consistent with the information that you have. And we can say that we can have a reward model to say, okay, this looks like a scientifically reasonable diagnosis, and we can use that as a reward signal for training. And this is a paper basically where they talk about that, sequential diagnosis with language models, and they design a scenario. They have cases, I think 304 cases, where you get the input. Okay, you have a patient with a sickness, and the AI is supposed to give a diagnosis for that through a couple of steps. The agent needs to check with the lab results. They need maybe to ask follow-up questions with the patient and so on until it has enough information to actually do a correct diagnosis. And interestingly enough, they say that OpenAI's O3 were able to make the correct diagnosis in 80% of the cases, and they compare that with proper physicians that only could do that in 20% of the case. So already here, even though it's a very limited domain, very limited data set and so on, we see that, okay, doctors are not maybe that good. And a model that is able to reason logically from the available information can do better. But okay, for this kind of economically valuable tasks, we need to have a lot of human data. We need to have the diagnosis cases, and we need to have a way to validate that the output or the diagnosis was correct in some sense. So human feedback or AI feedback. Okay, I'm running a little bit short on time, I think. So okay. Okay, let's go through this one as well then. So the question, one big thing also that is talked about is how reinforcement learning generalize. And okay, we have this paper that came out. There's a lot of papers from summer last year, but they are good representatives. There are more recent research if you don't think that's recent enough. But does math reasoning improve general LLM capabilities? Understanding transferability of LLM reasoning. So let's say I train a model on a verifiable task, which is, let's say, math, and the model learns to reason from that. That's how DeepSeek was trained. And then you could say, okay, if it's able to reason about math, will it be able to reason about other tasks? Let's say medical diagnosis, because that's also a reasoning task. I have some information, I need to break it down step by step, and I need to think, okay, what facts do I have and what conclusions can I make? And in this paper, they show basically that there is some good indications that reinforcement learning can generalize from specific domains into other domains. Yeah, and this is very similar to how pre-training was made. Basically, you put all the data into the pre-training data set, and the model knows a lot about everything. And if you say, I train it on instruction following, I can then say that, okay, instruction following will generalize to all the domains that were in the pre-training data set. This is exactly the same way that you train on model on logical reasoning, and since all domains were in the pre-training data set, the model will be able to generalize to reason about all the domains it saw in the pre-training data set. I think I'm not convinced that's true, but at least that's what the hypothesis here, that I can just teach the model to reason and it will be able to reason about everything to some extent. And here reasoning is not proper reasoning, it's not philosophically what we would say as reasoning, it's not really what you talk about as reasoning in reinforcement learning either. We can say longer computation or test time compute, but anyway, to some sense it's reasoning. So there are some indications that models will be able to generalize if you train them on a subset of all economically valuable tasks with a good prior model that has a big and wide pre-training data set. There's a big chance it will generalize to more economically valuable tasks than we had to begin with. Okay, so I call this simulation environments. Current style LLMs provide us with a lot of data. We're definitely not out of data, and there is a clear way forward in order to improve the data sets. We know from math and coding, we can use a lot of math that is out there, and with coding, we have like GitHub and so on. And for these more specialized tasks, we can create policy documents, so we can create the data that would be necessary for human feedback. And we will be able to make the models learn a lot of the different tasks that we have. So is this enough? Is this feasible to get to the economic Turing test in a reasonable amount of time? I think there is an interesting hypothesis called the big world hypothesis, came from Sutton, basically to say that the world is too big that, and dynamic and non-stationary and so on, that even if I restrict my data set to fixed, like I try to put a lot of it in, and I have this kind of generalization and so on, I'm still not able to build a model that will generalize to the real world. I mean, if you're philosophically interested in this kind of questions, you should look that paper up. But I mean, maybe 50% of all economically valuable tasks is not that big. So it's not really related to the everything that's in the real world. It's a lot about coding, customer service, you know, medical diagnosis, and so on. Maybe there's enough. Maybe that's 50%. So I have this hypothesis, and now we're coming into the conclusions. Basically, what I called narrow AI squared. So this should be a squared under the sign or the thingy there. So, and you all remember narrow AI is when we train classical machine learning models on a specific task. It's like predicting the credit risk of someone or predicting how much electricity will be consumed or stuff like that. That's narrow AI. And with these techniques now in post-training, we can square that by creating data sets that is relevant for all different domains, and we can include that in the language model. So you would have a system that has implementation for all the tasks that we wanted to be able to solve. And this we can do from preference data sets for reinforcement learning from human feedback. We can do verifiable subtasks like math and coding, RLVR. We can create simulation environments for agents, for coding and finance, customer service, and so on, and use these techniques to add all those narrow AI use cases to my model and potentially solve the economic Turing test. I think in terms of predictions, my feeling is that this is what the big labs are trying to do right now. So a lot of the money goes into collecting these data sets to create these environments and so on, to be able to check the boxes for all the different domains that are economically valuable. And it's just about the question of getting the data and then scaling up the compute. Okay, so what is the cost for that? Okay, I took this Pro RL paper, and they had, you know, 130,000 tasks, and they also said how much compute they spent on it. Basically, you say, okay, we can take 10 tasks per GPU hour, and one GPU hour is approximately $2. So if I have $50 million, I can basically train my model on 250 million different tasks. These will be fairly simple tasks, like solving a simple equation, solving a simple language puzzle, something like that. But we can then use a technique like R2E-Gym, take all the code on the internet, and we can create hundreds of millions of tasks on public repos, as I said before. And reinforcement learning is expensive, so this is what people do build these data centers for. And coding is the new scaling frontier. Pre-training is over, but coding is a new domain where we have all the techniques, and the labs have already started to scale that up. And that's why what we're seeing. Good. Yeah, I think I will stop there. I mean, there is some more material, and we can discuss it and so on. But I think, I hopefully made my points clear.
Coming to you, thank you so much, Josef.
Thank you.
Thank you so much. I think there will be many questions, because, as you said, there is more material. I think you have done a summary for us and that scratched the surface. So now we have quite a long time, if we want to be able to have a discussion. So I would be so happy to start with any questions that you might have. I can see that there are a few questions here in the screen from the online. I need a second first to check that out. Are there any questions here from the audience? Otherwise, I will start very gladly. So, if, as you told me also very recently, if intelligence is about solving tasks, that have not been seen during training. Are we currently overestimating what post-training can do without new forms of experience? In other words, are we stretching generalization rather than changing the nature of?
Okay, yeah. So, I mean, Sutton, for example, the big person behind reinforcement learning and one of the pioneers, he came out recently. They have, together with David Silver, that is currently behind DeepMind and also AlphaGo Zero and so on, they have this theory of the age of experience, that in order to scale models more, this kind of static scenario that I'm talking about, with just the fixed data sets, is not enough. And we need to have models that actually can learn on the job. Because these models that we have right now, they have static weights. And each time you wanted to solve a new task or learn a new thing, you need to put that in the post-training mixture of sets, and you need to retrain the model and push a new model out. And that's not going to scale as in the big world hypothesis to everything that the model can see, or actually what more realistically potentially could be 50% of all economically valuable tasks. So what a new domain, a research domain that I think is very open, and which is also why Ilya Sutskever recently came out on a podcast to say we're in the age of research, is that we don't know how to do that. We don't have techniques that can help a language model learn from experience. There is this thing of catastrophic forgetting, for example, that if you update the model in a non-controllable environment, there is a big risk that you actually get a worse model out of it. And gradient descent is a very disruptive technique that can screw up things. So if you don't believe that these post-training techniques are enough, we need to solve that. We need to have techniques to actually learn from experience. And I think there's a lot of people thinking about that, but I haven't seen anything that is close to being applicable.
Not within the next year?
No, absolutely not within the next
year. For a prediction.
No. Okay, we haven't talked about AGI, but this is, of course, a talk about AGI. And that's also why people say that, okay, AGI is still 10 years away from here. Because if you believe that you need to have a system that is generalizable and can learn from experience, and you believe in the big world hypothesis in some sense, then we need to learn, and we're not close to that.
Thank you. I must take a question from online, and sorry for approaching the screen here. We have Liju asking, while current agents are largely built on general language-based transformers, many real-world tasks lack a precise grammar for actions and feedback. Do you believe we are entering a phase where the primary challenge shifts from model building to an interdisciplinary effort of formalizing domain-specific tasks, protocols, and languages for LLMs to learn with reinforcement learning?
Yeah, absolutely. I think that's a super relevant comment, and I think my example with the printed circuit board is a good example of that. So you take a task, some very, very domain-specific task, and you turn that into a problem that is amendable to reinforcement learning techniques. And of course, for a lot of domains, you need to have domain-specific experts in order to do that. There was necessary to have experts to design the circuits that you can train the model initially from, and that environment of having this Zener language is also something that experts need to create. And I think with my claim here about the narrow AI squared is that we will be able to do that, or potentially it's just an engineering and a resource question in order to do that for each domain that are relevant. So creating these training environments for diagnosis, for customer service, for finance, for legal tech, and so on, in order to check them off one by one.
Thank you so much. Are there right now more questions from the audience here? Oh yes, we have a question from Jonas.
Oh, sorry. Yeah, not basing it so much on any specific publication or anything, but a lot of experiments within the project, for example, now, small scale pre-training I'm coming from. More or less like reasoning and this kind of stuff, but also instruction things. It seems that when we benchmark now, stuffing the data into the pre-training process is actually much more beneficial than doing post-training. Does that go against the kind of thoughts you have actually, or does it kind of coincide with that?
No, yeah. I think they will solve different problems, right? So in order for these models to be able to learn from reinforcement learning without the compute costs being prohibitively high, the fundamental domain expertise in some sense need to be part of the pre-training data set, because that gives the agent a prior, the agent knows about the problem from what it's learned from all the text on the internet. So if I'm in a domain, okay, so the problem here is everything is on the internet, so probably most things are already there. But let's say we come up with a new domain, I don't know, we have aliens. And there's a lot of new texts written about aliens that was not in the pre-training data set. To train a model to communicate with aliens, you would have probably to include that kind of domain knowledge into the pre-training set before the model was able to train through reinforcement learning without the compute costs being too high. But pre-training is also a very inefficient way to get the information out of that information. Okay. Is that an answer to your question?
To some extent, yeah. Yeah, we could definitely discuss that more. But
okay. So no, I think actually we have. Oh yes, yeah, please.
Other people talk.
Thank you. I think your talk. I mean, you touch on the question of profitability in from the AI revolution by the question of how do you get return on investment here, and you introduce the Turing economic model as sort of you can begin to expect 50% return on some tasks, and I'm simplifying your talk a little bit to ask a question, and you're suggesting that these labs are now looking for where you can find that profitability. Where do you have verifiable data, for example? And you mentioned the medical sector, so there you can make a difference. But really, one of the core sectors is the actual software development space itself. So the AI revolution is disrupting and eating on itself in a way. So when you think about for developers, either you can see that you can use AI to solve a multitude of problems, and you can use it to scale your efficiency, and then you can sort of add this to your way of working, and the world will continue to grow. But what I think you're suggesting is that rather one place where you can actually and where you should start to replace and shrink is in the development space. There you can shrink 50% and get value or return on investment. So that's my question to you.
Okay.
And how you in a developer culture or in your scene, how you're reasoning around this.
Okay. First of all, I mean, my opinion is not that this is necessarily a good or bad development. I'm just stating what I think are sort of facts here. But what we think and what we have opinion about, that's another discussion. But okay, so the economic Turing test is basically the 50% of all valuable tasks. So that's sort of how big of GDP is people buying software. And because if I say, okay, 50% of the economy would just be people buying software or subscribing to software as a service solutions like Netflix or ChatGPT or Microsoft Teams in enterprise and so on. So that's what it should measure actually, consumption of the services that could be created by an AI. And if we say, okay, what will actually happen here is, okay, let's say we have every kid from 10 can create a new startup with Lovable. And that creates a completely new economy where people just buy exactly the kind of software that they like. I mean, I can have, something very, very particular. There was some kid out there that built that with Lovable, and you pay 200 SEK per month about that. Then that becomes part of the economy, and it's a task that was created by AI, so I would put that into my economic Turing test calculation of 50%. Does that make sense? So it's not really about the... Okay, there is a deflationary aspect to it that there will not maybe be that many developers that we need, and those will not have money to consume or things like that. So there is an effect like that. But I mean, the hypothesis would, of course, be that this create more value for people, that we will have more software that you can buy that is better.
Thank you very much. We have another question. I will take one from online, and then we'll go to our guest here. So we have David Ekstrand who's asking, I know that physical AI falls outside the scope of your talk, but conceptually speaking, isn't it a problem that the economic Turing test seems to be operationalized in terms that are top of mind for software engineers? Surely economically valuable tasks include things like mining, power generation, care, education, personal services, and so forth. So is there a risk for misallocation of resources and research if economically valuable task is defined too narrowly within the AI community?
Yeah, I mean, in some sense, I think that's a good point. I think most of the labs and maybe a lot of AI researchers, they are a little bit naive. And if you go back to the agent company, for example, where they basically, okay, you have a company, but it's AI researcher that's designed the benchmark data set, and of course it's a software development company that they try it on. So yeah, there's a lot of people that is outside of software, and there's it's just that the real world is so much harder. But I mean, I have no numbers. I think you need to talk to an economist about this. I mean, how big part of the economy is digital right now? And of course, a lot of work is maybe, let's say you're in a mine, and 30% of the work created there is going into the mine and getting the material, and maybe 70% is getting the contracts or having the employee management, or I don't know. Then a lot of that, even if it's a mine, a lot of the work that you do as a mining company is still digital. So you will be able to take that part out. But I think it's, yeah, probably a lot of people are naive here about how much of the economy is actually, I mean, yeah, that we can turn into a reinforcement learning problem.
Thank you. We can have a next question from from the audience.
Sure, Joachim Hedenstedt. One question. I mean, it appears that almost all of the research, at least in this area of language models, etc., is focused on really large models and to make them sort of solve all kinds of problems. Do you see any trends where people are actually trying to sort of use smaller models for more sort of business important, but you know, more narrow tasks, perhaps to, you know, reduce compute resources, power consumptions, and things like that, or is that not really the hot topic at the moment?
It's, I mean, from my bubble, you're always in a bubble to some extent. I don't know how big my bubble is, but in my bubble, that's not a topic of discussion. I think a lot of people are hypothesizing that that will inevitably happen because the compute costs of running these models for all the different tasks that we expect them to do is going to be extremely expensive. and electricity consuming. We're already at a point where there's not enough electricity for the data centers. You know, Texas said that we cannot have any more data centers because then we don't have electricity for the people living in the state. And you know, in order to solve that, eventually the models will have to be smaller, or the efficiency of the GPUs need to improve and so on. But I don't think that has happened yet.
Thank you. I will take another question from online. Solving the learning on the job task, so the long-term memory, is one bottleneck. What are some other bottlenecks that impede exponential growth of capabilities that will become relevant after we solve that one?
Okay, I mean, the data is, of course, I mean, it's not only about compute and building the data centers, but for all the non-verifiable domains, there will have to be humans that put together the data sets that we can build the reward models on and so on. That's definitely a bottleneck. And let's go to legal tech. I saw there is a comment about Legora in the comments, for example. For legal tech, if you're going to create a big enough data set so you can scale the reinforcement learning for that in order to really maybe be better than a lawyer, then you need to have a lot of lawyers actually sitting and writing down that data for all the different aspects of law, which is going to be, I mean, expensive as well, of course, because lawyers are very expensive. So that's for sure a bottleneck. I think, but I think most of the problems here are engineering problems. I think I read the researcher talking about this. They say there's basically no need for new ideas if you stick to this limited setup of post-training, and it's just engineering, and there is a lot of difficulty still in being able to scale up reinforcement learning in an efficient way. So that's also a bottleneck for how fast this can progress. But I remember that first Opus, the big anthropic model, was actually too big for them to afford to do proper post-training on the Opus model. So that's how expensive this is. and it took them a year to solve the engineering challenges to be able to train Opus on all the coding tasks that they wanted to do it on. So that's why the Opus 4.5 model came only now, while the Sonnet equivalent was a year before or half a year before. So that's the engineering is definitely a bottleneck here.
Thank you. Do we have a time, I'm asking production, for 2 more questions? If I can only choose one, I need to go with the, okay, perfect. I have time for 2 questions, so that I can actually slide in mine. You know that I'm really interested in evaluation in general, and I'm thinking of evaluation after the pre-training area, or anyway, as we move away from the pre-training gains, let's say. Do you think our evaluation methods are now lagging more than our models? And are we still measuring the wrong things for post-training and agent-based systems?
Okay, so one area that I'm very interested in is, of course, AI safety. And how we evaluate how safe these models are. And is a very, I mean, to some extent, underdeveloped area, especially outside of the labs. And I mean, I will include AI safety in terms of evaluation, because that's a big part of it. And okay, we know that OpenAI and Anthropic and Google and so on, they does AI safety testing internally, and they have some partners to do that and so on. But I mean, it's not something we, as in the AI Sweden, cannot go and AI safety test a language model that came out, for example. And there's a lot of issues with, you know, potentially backdoors, or you know, this hidden patterns or hidden behaviors that potentially could be in a language model, or you know, racism or political bias or things like that. That I think it's a very underdeveloped area. But
so we're lagging.
Yes, we're lagging.
Yes.
But it's also the fact that people, you have this famous quote from Zuckerberg, "Move fast and break things." that's the name of the game. Wow. So people don't evaluate that much. You just shoot it out and see if it works.
Then I think I have the perfect comment and question from online to actually finish.
Okay.
And so Fredrik is asking.
Hi, Fredrik.
Sorry.
No, go on.
Oh, I didn't hear. To really unleash capabilities. Okay, no, it's this one. It's not this one. Yes, it's actually the question of Guillermo, forgive me. If I understand correctly from your talk, post-training is going to become cheaper and more accessible. When do you foresee Swedish companies or smaller companies, not AI specialized, for example, starting to post-train in-house models? So I don't necessarily think that you meant that it's going to become cheaper, or yes,
Well,
cheaper than in the beginning.
I mean, it will become cheaper because the engineering is improving. But I mean, when do you foresee? I mean, my first answer is I hope it will be soon. I'm not sure it will be. So as the complexity or because the labs are already trying to do that, and we need to have some specialized domain in order for that to make sense. I mean, it's a question of generalizability and what the big labs are actually focusing on, and some unanswered research questions of how how different all these economically valuable tasks actually are in practice, and how much you could just solve by scaffolding and agentic harnesses. I mean, I don't know. I think it's a very
It's a really hard question
Yeah.
but thank you so much for asking that, and thank you everybody for being here, for joining us in person on site here and online, for your great questions. Thank you, Josef, very, very much.
Thank you for letting me come.
And with that, I'll end this event. Thank you.
Thank you.